Okay.
Okay, so let me just get a heads up. Can you confirm that you can see the slides now?
Excellent, thank you.
Excellent, great. I'll not keep track of chat, but if there is anything on chat that comes up, I might occasionally glance over and see, but feel free to interrupt me at any point here. One of the things that I didn't actually put in the slides, and so I'm just going to start off with this, which is, it's, of course, maybe I should give a little bit of a background about where we are on Atlas. So we currently have 139 of those femtobarns recorded data, and that was from the all the way through to run 2. So most of the data that we're looking at is 2015 to 2018. Most of the things I'll show you today are actually 2015, 2016 data only. The full data set analyses are just starting to come out at the moment. Well, some of them came out a while ago, but these sort of difficult analyses I'm talking about today, sort of more on the timescale of hopefully the summer or the end of the year. We're currently in a big shutdown. The big upgrade in this case for Atlas is going to be replacing the innermost end cap of our muons. So they're called wheels. And so it's a small wheel. It's really not that small. It's about 15 meters in diameter. And there's a strong Canadian contribution there. And at the moment, we're really cutting it down to the wire as to whether or not we'll be able to install both sides of this new chambers or not. But the plan is that by early to mid 2022, we should be getting collision, physics quality collision data again out of the LHC. The decision about the center of mass energy will be made at some point soon, actually, probably by March or so. Most of us are thinking it's probably going to stay at 13 TeV, but who knows? We don't really know. So that's the kind of context of where we stand at the moment in the LHC. Oh, and then the run 3 is going to start, so middle of next year until the end of 2025. At that point, we end the nominal run of the LHC, and then we have a 2-year, 2.5-year shutdown to bring us to the high luminosity LHC era. So my interest in computing in the analysis model is migrating between where we are now to how do we take 10 times the rate and 10 times the total integrated luminosity into the future. But I'm not going to be talking about that today. So let me see if I can get that right. What I'm going to be talking about today is a little bit something different than the standard things that we think about when we talk about LHC physics. And this comes, oh, here we go. Okay, that's fine. This comes in part because we haven't found a thing sticking out like a sore thumb. We found the Higgs, that's great. But now we have to start looking a little bit more out of the box. So the idea here is really that you've got the standard model, and then you've got another sector called the hidden sector. And if they're completely decoupled, that would be kind of useless because we'd never know. So we have the constraint that they should somehow talk to each other. So there is some mechanism which communicates between the standard model and the hidden sector. So it could be relatively simple. So it could just be a new U1 symmetry. So we will have an example about this, like producing a Z boson, a dark Z boson, for example. It could be Higgs mediated. So you've got couplings between the standard model Higgs and the hidden sector Higgs. Or you could make it as complicated as you want. You could make it QCD-like if you want. You can make it any amount of complicated, really. But generally, we look for the simplest ones. So I like the illustration that's on the right-hand side here because it sort of shows you a little bit. So all of those colors of the pencil are different models. So whether we're talking about split SUSY, RPV violating SUSY, or whether we're talking about dark sectors, hidden valley sectors, you can kind of put them all together into the same kind of thing, as in something that produces anomalous signatures at the LHC. So these could be R hadrons, they could be stable photons, they could be dark photons, dark Higgs. They could be any number of these new particles that would potentially, because they weakly coupled to the standard model, we could still see them in Atlas. So what do we need in order to get this sort of dark hidden sector approach? Of course, if they were strongly coupled, we'd have seen them. So we require them to be weakly coupled to the standard model. And generally speaking, that gives rise to long-lived particles or unconventional type of signatures in Atlas. So in order to get that weakly coupled to the standard model, you need one of three things. Either you need a full small phase space, so things with masses that are nearly degenerate with themselves, with each other, or you get a very small coupling. So you look at rare decays of the Higgs, for example, or you look at highly virtual intermediate particles, so things that are very, very off shell. So that's just one example down there that I stole from somebody's slides. In all of those, you need really non-standard reconstruction and background estimation. So experimentally, it's a lot of fun. Part of the reason I like top physics is because it's a complicated signature with lots of things happening in the detector and all kinds of objects. And that's also why I like these long-lived dark sector type searches. If we think about it on the right-hand side, this is stolen from David Morrissey. In the dark sector portals, you can kind of have three different ideas. So you can either have the neutrino portal, so you have an exchange of a spin 1 particle. You can have a Higgs portal, so an exchange of a spin 0 type object, or a vector portal where you have a spin 1/2. So vector portal examples would be dark photons, where you've got couplings then to the standard model fermions. Higgs portal will be a dark Higgs. And then neutrino portal will be sort of some of these sterile neutrinos that mix with the standard model neutrino. So I'm not going to talk about that one, but I will talk about something neutrino related. So when we think about it experimentally, I'll show you one search which is not this. One search which is actually able to do just using standard Atlas objects. You can still be sensitive to these hidden sector models, because depending on the lifetime, you can actually still get the particles decaying actually prompt in your detector. But generally, because of that weak nature of the coupling, you will get particles that are produced that are non-standard model particles, so don't interact with the detector, that have a finite lifetime. Finite lifetime means, of course, they're produced at the primary vertex and they decay somewhere else. Now, if they decay outside of the Atlas detector, then we essentially see them as missing ET, and we can't really do very much about it. So really the range of sensitivities are talking about lifetimes from sort of millimeters, because we need them to be significantly, not quite compatible with B physics, or else you get a big background from B physics. So we're talking usually 5 millimeters all the way out to the end of the muon, or things that decay inside the muon chambers sort of at 7-8 meters from the interaction point. So this picture here shows you a few examples. So you could get, for example, displaced multi-track vertices. So you end up with this sort of signature, you get nothing, and all of a sudden you get a whole bunch of tracks appearing out of nowhere in the middle of your tracking detector. The next one listed here is a dark photon. So you actually get a photon in your calorimeter, no track in the inner detector because you don't expect one because it's a photon, but the photon and the structure that you see in the electromagnetic calorimeter is actually indicating that the photon didn't quite point back to the primary vertex. So the timing is a bit off, and the angles at which the decays happen don't make it come from the primary vertex. You can look at sort of displaced jets. So, jets of particles that come from, for example, inside the inner detector, or they could appear, for example, in a hadronic calorimeter like this trackless low EM fraction picture. So I'm going to talk to you about this analysis. You can then also look at them appearing in the muon spectrometer, or you could look at sort of funny things where you've got 2 leptons but that appear out of nowhere. There's a whole other class that you can also look at that are sensitive to these models, and these are when you look at things that are delayed. So these are very massive things, so they propagate slowly. So instead of seeing them as some particles appearing out of nowhere, you actually see them either in the wrong time. So they, for example, they decay the magnetic monopoles, they get trapped in the detector, and then they decay when there shouldn't have been a collision. So these are interesting to look at from a pure trigger point of view. How do you select them? How do you look at background? So you can look at them without a time. So when they decay outside of the standard window of when we collect collisions. But I'm not going to talk about them at all today. Right, so why do I think they're fun? So first of all, our standard triggers most of the time don't pick them up. So we need to develop. So this is really up to you. Think of an analysis, you think about what you want, and then you can start collecting the data. Most of the time, most searches you can use one of the standard triggers on Atlas and it will be good enough. In this case, you really have to start designing the analysis before you collect the data. The idea here is that it has to be small enough rate that it can fit in. that in the trigger menu, right, we've got a certain amount of trigger bandwidth that we can have. So we have to convince our colleagues that this is a worthwhile signature to look at and that we are allowed this bandwidth. You often, in order to get the trigger rate down, you'll still need to look at a prompt particle. One example that I'll show you is a prompt lepton, which is used for triggering, and then the displaced part is used later. The out of time things, you can use something that triggers like not in a collision, but the bunch after, for example. One example you can use, for example, timing information in the calorimeter layers already at trigger level, which is definitely not standard ways to do it. Another reason why you want to do this and keep the rates low is because most of the time you can't just put it through standard reconstruction. So this means you need to run some way in which the detector wasn't really designed to do, or the reconstruction system wasn't really designed to do it. So in order to do that, of course, we can't just say, please reconstruct all the data with this very complicated setup, which takes time. So we need to design filters. So on top of triggers, which is how to select the events, then we need filters, which is which of these events we want special processing of. And then either the trigger or the filter, you've just lost the event, so you can't really come back again. So for examples, if you have decays that are not from the primary vertex, well, this is a problem because all our standard track reconstruction relies on constraining the tracks to come from the primary vertex. This is very, very good at rejecting fakes. But that doesn't work if we explicitly are looking for particles that aren't coming from the primary vertex. So this is what we call large radius tracking. And so what we do there is we run standard tracking, and then we say what hits are left over in our detector. And then we run as a second pass this large radius tracking to try and see if we can collect any other tracks that are there. This is something which is not yet, there's no published information yet about this, but this is something which is actually going to be run by default in run 3. So Matthias Dunninger and other people have worked very hard on this over the past year, that actually it is possible now to run this large radius tracking already in the standard reconstruction. So from run 3, we won't have to do this as a special pass. Right, so now you've got tracks. So now how do you build displaced vertices? So then you need a custom displaced vertex. So, okay, so sure, we know how to do displaced vertices. We can just use B-physics, right? That's fine. Well, not really, because B-physics, they are usually from inside the first layer of detector material. They are high multiplicity, so you've got lots of charged particles coming out of them. So it's not really the same. So in fact, here is one of the things where you really need to design this analysis specific. So for example, if you have a SUSY search, then you've got these massive, very heavy, long-lived particles, and then they decay. And because they're very heavy, they're moving relatively slowly. So the angular separation between the decay products is going to be relatively high. Whereas the search I'll talk to you about today with the heavy neutral leptons, it's a very low mass thing that's produced. And so the particles will actually look like they're almost coming from the primary vertex. So depending on the search you want, you actually need to optimize your algorithm for what you need. Of course, one obvious thing is, well, how about if you've got jets appearing in the muon system? Well, clearly that is not how our muon detector was designed to work, right? Our muon detector was designed to have standalone muon tracks, which is one of the features that CMS does not have. So we can easily run that, but we don't really have the same requirements. And in fact, inside the muon system itself, there is a requirement of the track more or less coming from the primary vertex. So also, when you want to look at muons, even though you have the ability to reconstruct only with the muon detector, you still need to run something a little bit differently. One example, which is now, let's look in between the two, those are our calorimeters. So inside the calorimeters, then you can have different things. You can have low EM to hadronic fraction. So if you're looking at things that decay in the calorimeter, you'd want to maybe say, well, let's make sure there's not much energy in the electromagnetic part and most of the energy in the hadronic part. So it's kind of got a weird signature, and maybe the timing's off as well. But once you start talking about timing and layer information, you also have to start worrying a lot about detector noise. So we know that unfortunately our calorimeter is prone to having both actual detector noise and electronics noise, which causes these huge spikes of fake signatures of energy coming from particular layers. So they could be potentially striking. If they happen in the outer layers of the calorimeter, it would look like a striking signature. All of a sudden, a lot of energy deposited at the outside of the calorimeter. I mentioned timing a couple of times, so this is also something which is incredibly difficult to simulate properly, but can be extremely powerful when trying to separate signal from background. One other thing that we do, so that's those are the real experimental challenges that we have in terms of how do we even get at these objects. Then the problem is, how do we actually simulate them? So these are not so available. You can't just say, hey, Atlas, run this Monte Carlo for me. So you spend a lot of time discussing with theorists, getting these UFO type models, which is these unified format objects, I think, which are basically ways in which you can get new theory models into a Monte Carlo generator that we can then run ourselves. Right, so much that signal, but then when we talk about backgrounds, they're also sort of by construction non-standard. So you get things that, for example, top physics, you never have to worry about. So pile up, okay, sure, it affects everybody, but most of the people just use the standard pile up projection tools. Okay, you remove this amount of energy, good enough. Well, of course, pile up could actually mimic your signatures in some case. We have collimators a certain distance away from Atlas, like 20, 30 meters away inside the cavern. Maybe protons hit those collimators and produce a whole bunch of muons. Those are beam-induced backgrounds. And those muons then traverse the detector. If they happen to miss the inner detector, then they'll leave striking signatures of leaving energy mostly in the calorimeters. Then you could get cosmic rays. So if you're looking for something, well, is it a displaced mu-mu event, or is it a cosmic ray that just kind of bends a bit funny in our detector? Of course, we've got standard model backgrounds, so like long-lived standard models, so J psi's, upsilons, things like that. So this is more backgrounds that B-physics people are used to dealing with, but we're not really used to dealing with at that point. And then our modeling of our material interactions. Is our material model really good or not? And that will determine, for example, how many material interactions you get. It's particularly in the tracker that's important. I mentioned electronic noise as well. And so the outcome of all of this is that many searchers have to use as much data as possible to get these backgrounds. So we can't rely on our simulations to simulate beam-induced background. It's orders of magnitude off. So we just can't use that. It's maybe good to get an idea of whether your cuts work, but not at all to get an idea of whether you have half an event or one event estimated in your signal region. So lots of control regions, lots of regions where you have to validate your model, constrain your backgrounds. And in the end, a lot of these searches end up with a very small number of events, which makes it challenging from a statistical point of view. But I'm not going to go into the statistical side of things, that you're welcome to, of course, to ask me anytime. Right, so this is a plot that came out in the middle of last year. What it's showing here each row is a separate analysis that's looking for displaced particles in Atlas. And what you see with the bands is what is the region of C tau, which is excluded by that analysis under various assumptions. And so you can see, the only point I'm really trying to show here is that we're looking at sort of millimeter level through to meter level decay lengths. So that's the sort of range in which we're sensitive. Now you can see some of them that are more on the low end, and those are going to be prompt type of decays, or the ones on the high end are going to be things that appear in the muon spectrometer, for example. So highlighted, I've got the few things I'm going to talk about in more detail today. And there's a bonus that doesn't feature in here, but I thought was fun to present, which is a heavy neutral lepton. So of course, the bias that I'm using is a Canadian bias. So I'm going to talk in detail about a couple of analyses. So the first one is this trackless jets, which we call the cal ratio analysis. So the picture on the bottom shows you the sort of signatures we're looking for. So we're looking for nothing in the inner detector, nothing in the electromagnetic calorimeter, but all of a sudden a very large energy deposit in the hadronic calorimeter. So the main model probed in this case is actually that top model here. The other two models we could potentially interpret, but in this particular paper, we haven't done the interpretation of those two, though some theorists have done it for us. So essentially what you're talking about here, so you've got this proton-proton collision, and you're producing this, this scalar phi. So this is you've got two new particles. One is the Higgs-like. If it's low mass, it's Higgs-like. And then decaying to two scalars. Each of the two scalars decays to fermions, typically Bs, but we don't really care whether it's Bs or not in this case. And so the range that we're interested in is in the decay, the range of this scalar. So how long does this scalar live? In this case, we've got two separate optimizations for the analysis, one which is targeting the high mass and one which, so the high mass of this phi in this case, and one which is targeting the low mass. So of course, depending on the mass, you've got very different kinematics there, and you'll see that in a second. So the range that we're probing is really quite high. So this phi goes from the Higgs mass all the way to 1 TeV, and then the scalar mass goes from 5 GeV all the way to 400 GeV. And we're able to do that all within just decays in one slice of the detector, so just in the hadronic calorimeter. Unfortunately, I can't show you the full run-2 analysis because we're busy working on it. There's some interesting challenges, but one of my students is going to have his PhD on this. And this is an analysis that's done together with University of Washington and some colleagues in London as well. Oops. So I mentioned the first thing that you need to do is a trigger. In this case, we need two different triggers, one that targets the low mass and one that targets the high mass. In the end, you just basically need to figure out what's the best way we can do it in order to get the sensitivity. So the high ET trigger is fine. You just basically get a tau trigger. So you look in a tower of 0.2 by 0.2 in delta R, and you look for relatively high momentum. And that gives you relatively good performance because in fact our decay products look kind of a bit like taus really. If you want to get back to that low PT, so the low masses of the phi, then we need a dedicated trigger. So this is something that was able to be done after the upgrades that went into run 2. And we have what's called a level 1 topological trigger. So before in run 1, we could only select one object, or we could say 2 taus, or we could say 2 jets. But what we couldn't do is say, what's the angle between two things? So that's what we mean by topological in this case. So you can look at angular separations between objects, and so that's what we do. So we look at things with high fraction of energy in the hadronic calorimeter, and we look at angular matching between the hadronic calorimeter and the electromagnetic calorimeter. The HLT, the high-level trigger, is not that special, so we don't need to talk about that. So that first plot on the left-hand side here in the middle shows you the range of sensitivity. So this is the truth LXY. So this is based just on simulation. This is in the direction transverse to the beam pipe. Where are we finding some acceptance? So we've got the efficiency on the y-axis, and you can see that we're basically sensitive between 2 and 4 meters. So this is the actual where the particle decays. It's not C tau, this is where the particle decays. So we pick up decays between about 2 and 4 meters. Then the top right-hand plot is showing you, well, where do we pick it up in terms of momentum? What's the momentum of these long-lived particles? And this is where you can see why we need two triggers. So the full dots here have a much higher efficiency at very high PT, but it drops very quickly down at low PT. So that's why we need to recover the open dots, which is the low PT trigger. It's really not great, right? You can see but it's better than 0. It's better than what we have. So it's not the 80% that we get for the high ET, but we're going from sort of 0% at 50 GeV to 20-something% acceptance or efficiency. The y-axis is wrong. It's acceptance times efficiency. And then just the bottom plot to give you an idea. So this is just to show you where the samples should exist. So you can map. What do we care about high PT? Well, we care about high PT if we're talking about high masses of both the scalar and the phi. And if we're doing at the low PT region, then we're really targeting these sort of more Higgs-like phis and the low masses. So in order to get any sensitivity to the Higgs-like, we need these extra triggers. Okay, so then what do we do? Well, the first thing you need to do is determine whether or not we can actually reconstruct this vertex. So where is the origin of these particles? So you can see here, this is done with a multi-layer perceptron, and the two plots are showing you, again, where it physically decays on the x-axis that we know from Monte Carlo where it decays. As a function on the y-axis is where we predict it to decay. So what does the multi-layer perceptron, the MLP, predict it to be? So It's not great, but it's really pretty good. And then the bottom one is just showing the same thing for the z-axis. So that's the first thing we do. We say, okay, tell me where it comes from. And then feed all of that information as well as track variables, jet property variables, moments, layer fractions of everything, and put it into what we call a per jet BDT. So everything inside this big jet cone, feed it to a BDT, and what do you get? And in particular, you need to worry about three things in this analysis: signal, QCD, which you'd think, wait, but this is something appearing in the calorimeter, wouldn't QCD have tracks? Well, yes, QCD normally would have tracks, but there's a very, very low chance that you get almost entirely pi zeros or neutrons, and then you just don't pick up the tracks. So it actually ends up being a big background for us. And then the third one is this beam-induced background. So this is where you can see the three plots are showing you the signal weight, so how signal-like it is. The middle one is how QCD-like it is, and then the right one is showing you how beam-induced background-like it is. And you can see the open black blobs of the beam-induced background. It's not great separation, right? But if you put a cut at like 0.34 or something, then most of what you've got above it is going to be mostly beam-induced background. So in order to really separate signal from background, you need these three components, carefully looking at it. Okay, so then we've got that. How do we actually put it all together into an event selection? And the answer is you put the output of the jet selection, because we've got two jets in our model, and so you need two of those things that have a high score, and you want to still keep other variables. So for example, oh, sorry, I jumped ahead of myself already in what I'm speaking. This slide is actually, I wanted to spend a little bit of time on it. Sorry, I did it last night. What variables contribute to this per jet BDT? So these are the ones that are shown on the bottom. Some of the obvious ones is, well, look at the tracks. How many tracks are within 0.2 of the axis of your jets? Well, of course, QCD, you'd expect a lot of tracks. But you can still see, even if you look at very low PT, you've got a non-negligible background from QCD. But it's a very good discriminant to reject QCD. This middle plot here is showing you the timing difference between the leading jet cluster, so the highest PT jet cluster, and the timing you'd expect if it was a beam-induced background muon originating from the positive Z direction. So hit the collimator in the positive Z, and what timing would we expect it to be? And so you can actually see this is actually out of time compared to in time. So muons that are produced at the actual same collision that you're recording or at the next collision. This is a very nice example on the right-hand side of showing why BDTs or any machine learning is actually really good at exploiting correlations. Because when you look at just the projections, sure, it looks like there's some separation. But when you look at the two-dimensional distribution of the position of the cluster in Z, so in distance from the primary vertex along the beam direction, you can see a very nice structure. So things that are not beam-induced background will tend to have a timing close to 0 independently of their Z position. Whereas the bottom plot shows you if it's beam-induced background, it has these really kind of cool little features. And these features, if you can see, I don't know if you can see, these dotted ones come from in-time pileup. So this is when the beam-induced background is happening in the current collision. The dashed ones that are coming up here are coming from things that are happening one bunch crossing earlier. So the beam-induced background happened earlier and is coming through the detector. And then you can't really see much in the data itself, but the thick black lines at the top are actually showing next to next. So we're actually sensitive to picking up things that are coming from two bunches away. So this is a nice example of exploiting correlations using machine learning. So then you sausage factory it all together. You look at all the different variables that you have, separation between objects, things like that, and then you put it into what's called a per event BDT. So this is event level, you want two of these jets. And here again, you can see there's relatively good separation between the signals in the colors and then the data in black and the beam-induced background shown in the open circles. So you can see we dominated here, and there's not much evidence, there's no evidence here that we've got a bump consistent with a signal. I'm going to skip this gory table. And then after all of that, what do? Well, we we don't have enough events to actually do anything very clever. So we do what's called an ABCD method. So we take regions where we expect almost no signal. So for example, there's this D region, we expect almost no signal, and then BC. So you want two variables that are orthogonal or independent of each other as far as you expect your signal to be. And then you can use a ratio of events in two regions. You expect the ratio here, for example, of C over D should equal A over B. We put it all into a simultaneous likelihood fit, and we get that table on the bottom. We're talking really low stats here. So even in our regions where we're extracting the normalizations, we're talking about 9 events or 2 events, depending on the selection you have. Region C and D have higher stats, but we're still talking about hundreds or so events. And unfortunately, when we unblinded, we didn't see an excess of events in the region, so we put limits. I'll skip this page, and go straight to the limits. So in this case, we interpret our limits as a function of cross-section times branching ratios, and this is the branching ratio of the phi to SS. And we look at what our data is able to tell us. So if we had, for example, 100% branching ratio, we would put a limit at where this curve is, so where this blue line hits our curve. So from basically 0.1 meters all the way up to 10 meters. So that would be our limit if you want to make just a 1 number. So the bottom plot is showing you basically how it evolves, how these mass limit changes as a function of the mass of the scalar for a fixed Higgs mass. You can make all kinds of plots based on these. Something that's shown, so for example, for the high mass selection, this is choosing one particular point. So it's 600 GeV for the phi and 150 GeV for the scalar. And you can see the improvement over the previous analysis. So this is a huge improvement by over 2 orders of magnitude, basically, compared to what we were able to do before. So this new trigger really, really helped us get acceptance to that high mass search. Okay. One slide that I'm going to skip because there's another analysis that fits together with this one where they look for decays in the muon spectrometer, but I'm going to skip that. There's no Canadian contributions. Right, the second search I wanted to tell you about today is a search for what's called Z dark, or production of a Z and a Z dark. So again, this is Uvik and York playing leading roles in this analysis. So this is an example where we can actually use mostly standard reconstruction in order to get at this signature. And the idea here is that we only have very weak constraints on the branching ratio of the standard model Higgs, non-standard model case of the Higgs. And that's only something like 30%. So there's a lot of space for the Higgs to decay in non-standard ways still. So one example is you could use this Higgs as a portal. So you can extend, like the simplest way of extending an interaction between the standard model and the dark sector is just a single U1 gauge group. So if you do that, what do you have if you have a U1 symmetry? You end up with a single massive vector boson, which we'll call Z dark. You can have models with or without symmetry breaking, so you can get a dark Higgs type sector, which is the one drawn on the bottom. So you can get either hypercharged portals where there's no additional coupling to the Higgs, or Higgs portals where there's an additional coupling to the Higgs, and then you can produce a pair of these dark Z bosons. There's also an interpretation in the 2 Higgs doublet. In the end, it doesn't really matter what it is. There's 2 parameters that you need to worry about in your model. So either the kinetic mixing between the standard model and these dark sectors, so that's shown in this upper diagram, or you get mixing between the standard model and the dark sector Higgs, in this case of a Higgs portal. In this case, we actually have 3 channels that we look at. One is more targeting the top diagram, where we actually have a standard model Z and a new Z. So we call that ZX. Or 2 analyses that are looking for the pair production, so where you've got 2 new particles. And there's 2 actually that happen, one that's targeting the low PT or low mass, and one that's targeting the higher mass. As I said, this one doesn't rely on standard triggers because all you've got really in this case is 4 leptons. So you have 4 leptons in your final state, and you expect it to basically be very similar to ZZ production, just with slightly different PT. So you can just use standard lepton selection. In this case, because we need 4 of them and we want to maintain some actual acceptance in our signal, we need them to be relatively low PT. So we go as low as possible, as loose as possible definitions of leptons. We just need to have them slightly higher PT in order to pass our triggers. So we put cuts on the leading one, it has to be 20, 15, and 10, purely driven by our requirements on the trigger. And then you just play a combinatorics game, right? You've got 4 leptons, so how do you pair them up in order to fit your signatures? And that will depend on which signatures you're doing. But for example, in this case, you want to say, you define the pair, you call 1, 2, the one that's closer to the Z mass, and 3, 4, the one that's further away, just to label them. Another problem that you have, as I mentioned right at the beginning, generating Monte Carlos is not easy. In this case, it's always assumed that we produce by the dominant production, which is gluon-gluon fusion. So here's one analysis. So this case, you're really looking, you know there's a standard model Z, so let's use that one. And the other one, well, it has to be something else. So the 1, 2 pair, you put a relatively loose range, and then 3, 4, you put an even looser range. That's just to say, let's pick up most things. And then, of course, you need to make this one of the pairs very consistent with a Z boson. In this case, you can actually use data-driven backgrounds in yellow, which really don't matter very much. And then the other ones, which are irreducible backgrounds, are estimated from Monte Carlo. So what you can see in this plot is actually unblinded results, where you have the standard model production of decay of Higgs to a Z and an off-shell Z to 4 leptons. But that's relatively well known. That's well modeled, well known. So we're okay using that with a significant background. And then you can see the 3 sort of semi-transparent, which would be high ideas for different signals. So no signal is found, unfortunately, in this channel. When you want to talk about the pair production of these dark mediators, you want to look at a few other things. For example, you want to look at separations of the same flavor or opposite flavor. So you need to be relatively well isolated because you don't want to pick up a photon decaying to a pair of electron-positron, for example. And this plot on the top right-hand side shows you an interpretation of what it is. So you look at the mass of the first pair versus the mass of the second pair, and you can see the signal region here that we're going to pick up is that green band. So you want to pick up the combination with the smallest difference because now we've produced 2 of them. We're assuming it's the same particle that's produced. So therefore the 2 sides should be the same. We want to reject Z's. So that's the X's that are through those. So those fail our Z veto in this case. And then you have others that are coming from things that are more standard model, like over here, that which we reject because of our kinematic cuts. You also have to reject so that things like J psi, epsilons, and things like that. This one, again, you get your background from Monte Carlo. If you look on the bottom plot, what's the level of background that you expect? So in this binning that's shown here, you're looking at 10 to the minus like 0.1 events in each bin. So overall, you're really expecting a very, very, very low background. So you're almost essentially background free, except so what you see here is you can see 1, 2, 3, 4, 5, 6 events. Unfortunately, not consistent with a dark sector signal. The third one, I won't spend as much time on it, is basically we found no events, and this is looking at the low mass region where you have to worry about B physics, and so you have to put in cuts where you expect resonances from known standard model backgrounds. This is a case where we actually observed 0 events. So the limit setting here is a bit more complicated, but I'm going to jump to this one. So one of the things we do here is put a limit model independent-ish on just fiducial cross-section. So we define a cross-section in a particular region of phase space that makes sense from a particle point of view. So if you had your model, you could go and run your Monte Carlo and see what would be my fiducial acceptance. So what would be my acceptance at Monte Carlo at truth level, if you like. And you can put limits on what that production should be. And now you can see there's a couple of little excesses, neither of them particularly consistent on the global scheme of things. And those are what you actually end up seeing in this analysis. You can make it more model dependent if you want by putting in particular branching ratios, assumptions, and how it decays. Right, in the last 5 minutes that I have, I want to talk to you about the heavy neutral lepton. So this is one that actually we're heavily working on in Vancouver, but it's not in this analysis I'm going to present, but the next one that's coming in. So the motivation here is that, we know neutrinos are massive, so we need some mechanism to generate the masses. One idea of this is either right-handed neutrinos, Majorana neutrinos, or both. So we look at a case where they're right-handed Majorana neutrinos. So we call this a heavy neutral lepton. So there's basically, that's the standard model. Neutrinos acquire mass inversely proportional to this HNL mass, because that's how they get the mixing. So it's the mixing with these right-handed Majorana neutrinos that gives the standard model neutrinos their masses. And you can see over here, interestingly enough, this is a function of mass, and then the y-axis is coupling. But basically, you can see that most of the experimental evidence that comes from actual long, fixed target experiments, because you're looking at things sort of the order of below 5 GeV, you produce them in hadronic decays. So if you look at an experiment that's designed to look at hadronic decays, you can put constraints on there. But this whole region of phase space above a few GeV all the way to sort of 100-ish GeV is dominated by collider physics. So L3 and Delphi were at this point in there. So this is, if we want to target that higher mass, we really need to go to colliders. And in particular, when we talk about hadron colliders, we don't want to produce it in Zs, because we want to produce it in W to gain in cross-section and be able to trigger on these events. So this is the signature we look for. One example, so we produce a W from our proton collision. The W decays to, in this case, a muon and a neutrino. The neutrino mixes with this heavy neutral lepton and then mixes back to the standard model some physical distance later, and then decays, and decays via the weak interaction. So you get basically, in this case, 2 muons, or a muon electron and a neutrino. So you have a prompt lepton, and then you have a displaced pair of leptons. There are only really 2 parameters in this model. So the mass of this heavy neutral lepton, this mass of this N, and its coupling strength. That's why I showed you the plot on the previous slide. There's 2 approaches that were done up to now. One is targeting the sort of higher masses, where we look at the prompt signatures. And the other one is targeting that region between the collider, between the fixed target decays and all about 10 GeV. These lead to displaced vertices, and we can then probe down to much, much lower couplings. So this is what the signature looks like. This is a plot that one of my grad students made. So you look at the primary vertex, you have a prompt muon or prompt lepton, and then you have a pair of leptons that make a decay vertex. So as I mentioned in the introduction, you need to have your own vertexing algorithm in order to reconstruct this. You need to use this large radius tracking so that these particles are not coming from the primary vertex. And you need a filter. In the end, what you can see on the bottom is our efficiency to select these various particles. So the prompt analysis, where you just require 3 leptons from the primary vertex, is these black points. And you can see that the different masses for this heavy neutral lepton will have different cross sections, but in the end, what we're sensitive to here is decays from sort of a few millimeters out to a meter. So this is really things that decay in the inner detector. So the prompt is a relatively simple analysis in the sense that we obtain things from multi-jet backgrounds, so faking things that fake leptons as a dominant background. You can do a simultaneous fit and you don't have too much of a problem there. In the displaced, then you have to look at things from a first principles point of view. So in this case, the backgrounds are mostly from accidental track crossings. So not real vertices, but fake vertices. So it's just tracks that happen to randomly. So maybe they were produced in the primary vertex and they went like that. They crossed again, and then you reconstruct it as originating from there because you missed something happening from the beginning. In the end, when you do this, we have to reduce beam-induced background. We have to reduce our backgrounds from our J size and our heavy flavors. And you end up being able to estimate your background based on the number of leptons in this displaced vertex. In this case, we end up with 0 events observed, and we expected something like an upper limit of about 0.3 background events. So these are the limits that we look at. So in this case, the displaced analysis only looked in the muon channel. And you can see the comparison. So the prompt analysis is the one that extends to the higher mass, and how that compares to Delphi, and then CMS has an equivalent one. And you can see the limits are basically comparable now to what we were able to obtain in LEP. But now, of course, we have a lot more data on hand. Instead, the displaced is really sensitive to to lower masses and down to much lower couplings. How that translates in terms of physical distance, so you can look at this C tau on the y-axis on the left-hand side, and you can see again, so we're putting limits of the order from something like 0.5 millimeters all the way to about 40 millimeters in our case. So now let's see if we can put that on the same plot. So there's actually, I asked one of our German grad students to make this plot for me yesterday. So he put these limits onto a European strategy briefing book. Here the full lines are showing things that are in we have already. CMS line is also just recently published. And then all the other lines are basically future experiments that are coming online and that are sort of planned as part of this European strategy. So you can see that while we've got things like Methuselah, CHIP, and things like that, they're also fixed targets. So they're targeting, again, those low masses. But we really need to go to the FCCEE, so really thinking 30 years down, to be able to explore this whole region of phase space. But we believe that actually with an improved analysis strategy, we can start digging quite a bit deeper, both in slightly lower masses, slightly higher masses, and lower couplings as well with an improved analysis. Okay, I want to come to my conclusions here. So I hope I've convinced you that the dark sectors are fun to do at the LHC, and really there's a lot of room for improvement. So I expect over the next few years to see a lot of new searches, new ideas coming out. They're fun from an experimental point of view because they're challenging and they use non-standard tools. And I hope that at least over the past 45 minutes, I've convinced you that atlas analyses and LHC analyses generally are not routine, despite what some people might think.
Okay, thank you very much. I'm just going to, before we jump into the questions and the discussions, I'm going to